Okay, so let's start the class. So on Thursday, hello, hello. Thursday, what's happening Thursday? So the test is in person on paper. So for the test, make sure to bring your equation sheet. And before the test, make sure you go over the equation sheet and you understand every single equations that is relevant to the test, right? So make sure you understand each equation, what it means, and the units as well. Okay, so make sure you make sense of those equations and make sure you know how to use them. And if you think that you are missing some equations, just memorize them. Don't forget to bring a calculator and a pen. It's in person on paper. So remember that if you have a positive charge wants to go from high potential to low potential. Remember the DC circuit, the current always wants to go from high voltage to the ground. But a negative charge, such as an electron, wants to do the opposite. An electron wants to go from low potential to high potential. Because an electron is negative, it wants to go to the plus. You can think of high potential like being more plus than the low potential. Low potential could be the ground. Okay? And don't forget for the test, of course, conceptual questions, my tests are not very heavy in math. So remember to go over the concept like electric field, electrostatic field configuration. If it's a positive charge, the field is outward. If it's a negative charge, the field is inward. Okay? A positive charge wants to go with the field, a negative charge wants to go against the field. Okay? So anyway, let's start a new unit about magnetism. It's very useful if you go in biology or natural science. So you see here you have different magnets. So those type of magnets, they are called plug magnets. They are the one you can buy at Home Depot, for example. Like if you lose something in the sewage, you attach that to a string and maybe you have keys that fell into it so you can recover them. This is a very, very strong magnet. It's called the horseshoe magnet. It's very strong. These are the new ones. I mean, not new, but relatively new. They are called neodymium magnet, and you can build a geometrical shape with them, and that's a regular magnet. So let's see, let's start. Okay, so we're gonna cover all that. North pole. So magnet has two poles, so it's a dipole. Turns out, can we have a positive charge on its own? Yes. Can we have a negative charge on its own? Yes. But can we have a north pole chilling out on its own? No. The north pole always goes with its south pole. You cannot separate them. So it means if you take a magnet and you break them in two parts, you still have two magnets. You take a new magnet, you break it in two parts, you have a new magnet. So you always have a north and a south. Doesn't matter how hard you try to break it and break it and break it, you still end up with a north and a south. So you do have charge, like mono charge, a plus or minus, or you can have an electric dipole, like water molecules. So you have a plus and a minus that combine together. I mean, you have a plus here and a minus there, but you cannot have a magnetic monopole. If you find one, you get the Nobel Prize instantaneously, okay? And then you will give some credit to me. So they are still looking for it, but no, so far you cannot have a magnetic monopole. North repel, north attract south, okay? You all played with magnet. That's what got Einstein started physics. He was playing with magnet as a kid. So it's magnet comes back a long, long, long time, like in 1000, AD. Magnetism, magnet uh, comes from geographic area. I think it's in Greece. Okay, it's named Magnesia. So magnetism is named after that, where they used what is called loudstone. So loudstone is like if you take a geology class, you work with minerals, and one of the minerals you can work with is called magnetite. So these are natural magnet. Of course, at the time you didn't have like way to build them. So they are natural magnet, and they were used as compasses, especially by the Chinese, for example. Okay, so that was back then. It's called Loudstone. Okay, the one who really started to understand magnetism. His name is William Gilbert. Interestingly, he was the physician of. You remember that queen? She had red hair, like a thick layer of makeup because her skin was ruined with all the weird stuff they used to put on the skin. Elizabeth the First, right? Very interesting history. The British history is very interesting. They used to put mercury and lead on the skin, so her skin was terrible. So she had to put like one thick layer of makeup. And so anyway, I'm not going to take a tangent. So let's go back to here. So this doctor here, he was a contemporary of Kepler, Galileo, and he's the one who understood for the first time that the Earth itself behaves like a magnet. Okay, so I'm going to show you that in a moment. So let me do some demo. No, no. Okay. So you have a magnet. So that will be the north and that will be the south. Okay, so it's going to produce around it, even though you cannot see it with your eyes. What do you think it's going to generate? Magnetic field. Very good. So you have electric fields produced by charges, and you have magnetic field produced by magnet. Okay, so so of course here you see this is north and this is north. So what's going to happen? Repel each other, right? You see, so as long as there is a force, there's going to be an acceleration. Now, if you have south and north, what's going to happen? Attract each other. So this is a force. This is a force at a distance. But instead of thinking this that the magnetic force is going to grab this one and pull it toward or pushing away, we're going to think in terms of magnetic field. It's the magnetic field from this one that will interact with the magnetic field of that one. Okay, so here the magnetic field will push away, and here the magnetic field will make them pull towards. Okay, so if I have a piece of paper, I don't like to do that to my notebook. So remember for the test, if you have a positive charge here, what's going to happen to the electric field? It's going to be outward, right? So it's diverging away. And as you move away from the charge, the electric field is going to decrease. So it's following an inverse square law. Now, a magnetic field is different. You see, you have your magnet here. So you have a north and you have a south. But you see, it's like a dipole. Okay, so it's not going to diverge. a magnetic field always curls. Okay, it likes to curl around. It likes to loop around. It doesn't diverge. It doesn't converge. Remember, if I ask you on the test, if this is negative, the electric field will go in, wants to converge. Yes? And if you have a water molecule, so if you have a dipole, okay, so it's going to do something like this. That's going to be in, and that's going to be out. But from a magnetic field, it's going to be different. You're going to have a magnetic field going out of the north, back into the south. So those will be the magnetic field line, okay? Out of the north, into the south. See that? Out of the north, into the south. So this one, it always ends. So here you have the ground. This one has no ends. So magnetic field, if I ask you, always curve. Okay, likes to go in low. Of course, if you are very close, it's going to be strong. Farther away, it's going to get weaker. Do you see how it works? So you have different types of magnet. So for example, this one is a horseshoe magnet, and you can use giant one. Okay. So what do we use them? This is the what? North or south? North, and that will be the south. In between, you're gonna have a magnetic field from north to south, and then it's gonna loop around. But in between, you have almost like a uniform magnetic field. Okay, so when you have a horseshoe magnet, it still go from north to south, so it's gonna loop around. Okay, it's gonna loop around, always looping around. But in between, the magnetic field is almost uniform. Review for the test. Remember when you have a capacitor, okay, you have plus Q here, minus Q. Between the plates, you have a uniform electric field. Okay, and you can look at and you have a voltage between them, right? So you have delta V divided by the distance between them equals to the electric field in magnitude. So that's just a review. But here, the magnetic field will be almost uniform. So this is called the horseshoe magnet. Are you with me? Okay. So magnetic field likes to curl around. Never wants to diverge or converge. So, of course, it's going to be the same thing here. You see, that's because it's metallic. But you see, north will be repelled by north, and south will be attracted by north. Okay? So usually you don't leave a magnet like this, because otherwise it's going to lose its magnetism. So why is that? Because you see, in space you have the magnetic field, and inside that magnetic field you're going to have energy. So remember, for a capacitor, we talk about the energy stored inside that capacitor, and when you discharge a capacitor across the heart, for example, all that energy is going to be burnt out inside the heart. So likewise, inside the magnetic field, you're going to store energy. So if you leave your magnet like this for a very long time, all the energy is going to leak out. So usually you use like something to keep the magnetic field. So it's like a guard. Okay. So what you do something like this. Now the magnetic field is forced to stay inside here, cannot leak out, and you keep your magnetism because those here are not magnetized. Okay, so it's not like a natural mineral that you find in the earth. You have to make them. You have to magnetize a material, and after a while, you are losing the magnetism. Is that clear? Okay, so here you have different type of magnet. So for example, here you have those type here, and so in that case, the north is somewhere. Let's say that could be the north, and that will be the south. Yes. So if I take my pen, so this is south. What's going to happen if I put south? They're going to repel each other. You see? Isn't that cool? Can you see that? It's called levitation. Like in Japan, they have those special trains that they call maglev, and they go really fast, and they use that magnetic levitation. So you see that you can store energy into a magnetic field because you can do this. Look, I'm doing work here. And my work, where did it go? It went into the magnetic field. And if I let go, boom, the energy is released. Okay, so it's a type of potential energy. You can have also this type of magnet here, the Fridge magnet, and you can see that will be. So this is south, so this one has to be north, and this one will be. Ooh, you look how strong. So those you buy it online, you know, I bought it for demonstration, but it's very cheap and it's very crappy. But this one is stronger. Look at that. I can do that all day long. It's fun. So here you have some, it's called iron filing. So you take a piece of iron, you use like a file, so you break the iron in small pieces. And you see, you remember when you were a kid, you can do things like this, right? Isn't that fun? So let me ask you something now. What is that? Compass. But a compass is what? Yeah, you have a, yes, a magnet that will tell you the north, that will tell you the south. Let's see. If I bring another magnet, so this is the south, okay? It will be attracted to north. And I can do the opposite. That will be the south, and that will be the north. Now, let me ask you something. Do you agree with this? Right? So this is the south, and that will be the north. There's something weird here because this is the north, obviously, but it's also called the north-seeking needle, right? So if you use that on Earth, it's going to show you the north. So it means that at the geographic north, can we have a north? A magnetic north? No, because look, north is attracted to south. So that means the Earth is behaving like a giant bar magnet, but at the geographic north, we must have a south. Okay? So I will show you. So that was why I was telling you that, because it's that was found by Gilbert, who figured this out. But look, now my Gilbert is upside down. What did I do? Help. Where? Yeah. Ooh, thank you. Gilbert was upside down. Okay, so here you have a bar magnet. Okay, you can visualize the magnetic field. So do you remember how when you have a small dipole, it will align itself with the electric field line? Do you remember that? Okay, I forgot. If you have one question like this, I forgot. But anyway, when you have a dipole, like an insulator that get polarized, okay, with a plus and a minus, it will align itself with the electric field. Don't forget that, right? So here you have small dipoles, so they are small magnet or small compass, and they will also align with the magnetic field. Okay, let's see inside the magnet. So a magnetic field comes out of the north into the south you see, it's easy to get good grades for this unit if you pay attention, if you are using your listening ears, used to say my teacher. Use your inside voice and listening ears. So out of the north into the south. So you see how the lines are farther away as you move away, that's because it decreases. And you see here I have a compass. So north is attracted to south. And I go around like this. I go around, boom, boom, boom. And south is attracted to north. So now if you take the planet Earth, guess what? The planet Earth behaves, everything happens like inside Earth, you have a bar magnet, but the magnetic south is at the geographic north. So that's why if you have a compass, it will show you the geographic north, because here you have a south. Got that? So it's like a north seeking side here. Okay, so why is that? So you can start digging outside here. You will never find the bar magnet. Okay, it's just because in the outer core of the Earth, okay, remember your geology class? You have an inner core, outer core, you have the mantle, and then you have the lithosphere or the crust. Outer core is what, liquid or solid? So the inner core is solid because the pressure, right? Remember your chemistry class? If you increase the pressure, the molecules are not free to move. But the outer core is liquid. So it's like you have electricity flowing in that outer core, and we're going to see that the source for magnetism is electricity. If you have magnetism, it means that you have electricity flowing, or you have charges flowing, or you have ions flowing. So in the outer core, you're going to have iron, but it's what is called ions, like ion that have lost electrons. Okay, so it's charged, so it's flowing inside the outer core, so it's going to produce magnetism. Any question? Okay. So, anyways, so it happens like every million years, okay? It's gonna flip. So the south will be at the geographic south, and the north will be at the geographic north. We don't really understand why, but we have the proof that like every million years or so, the humes it's flip. Okay, and that's a problem because when it's flipping, so we lose our protection against cosmic rays coming from the sun. Okay, so the magnetic field of the Earth is actually protecting us. So let me show you what a magnetic field looks like in 3D. So 3D looks like this. So I show you 2Ds, but in 3D, it looks like that. Okay, so can you see that it's almost the same configuration that you have for an electric dipole? Do you remember an electric dipole? When you have a plus and a minus, you have the electric field going from plus to minus. Okay, that's a magnetic dipole. Same configuration. The magnetic field comes from the north into the south, back to the north. And as you move away, the magnetic field is going to decrease as 1 over the distance. You copy me? Good. So if you go back to the last unit, electric decay, you remember when you have a dipole, like in the water molecule? So oxygen take the electrons, hydrogen missing electrons, so this is plus, this is minus, that will be the configuration. So it's the same. Electric dipole, the electric field configuration looks like a magnet, a magnetic field from a magnet, bar magnet. Okay, is that clear? So our Earth, like most of the planets, See, I took that from my astronomy class. Earth, you see how it has a magnetic field, except that that should be the north and that will be the south. I don't know why it's upside down here. So that's the north, out of the north into the south. Oh yeah, because that's a geographic north, which is the magnetic south. So out of the north into the south. Yes? So it's a shield. Whoever, whatever made the earth gave us this shield against the solar winds and against the cosmic rays and all those very harmful particles coming from space. If we didn't have that, it will not have been possible for life to evolve because too much radiation coming from space. Other planets have magnetic field as well. So why is so important to have that magnetic field? You see, this is the Earth, and you see all those dangerous particles could be protons, could be electrons, could be, charged ions bombarding the Earth non-stop. It comes from the sun, from the solar wind, but it comes from space as well. Constantly, constantly. So the magnetic field is like a shield against those radiation. Some of them make it on Earth, of course, but the most dangerous ones are being deflected. Isn't that interesting? So if you can have like so this is called you see, I don't know if you did that in class, but you can make your own cloud chamber. Okay, so you do that with a plate, heating plate, and you put an aquarium like that upside down, and inside you put some alcohol vapor. Alcohol vapor, like you took chemistry, which is saturated, which means that that vapor is about to turn liquid, but not quite yet. So it needs a kick. So then you have all those particles coming from space, going through your brain. Every second you have particles going through your brain, right? So with this cloud chamber, and that led to a Nobel Prize, you can visualize those particles coming from space. Okay? So the idea is that you put some alcohol inside. So this is saturated alcohol. Do you see this one? Oh, here is this one. Look at that. You can visualize the track they leave as they go through the cloud. Why is that? Because the vapor is saturated, so when it's going through, it click. Oh, did you see this one? You see that one? Isn't that amazing? And the music. You can find that on YouTube, I think. It's called Symposium. Cosmic Ray Detector Symposium. Cloud Chamber. Okay, so let me show you another simulation. So I'm going to put iron filing. So iron filing are little pieces of iron, and inside the magnetic field, they're going to get magnetized. And if you do that, you can visualize the magnetic field. Instead, you can use compasses as well. You see, north and south, bloom, bloom, bloom. Okay. Are you still with me? So what's happening to those little particles coming from space? When they're gonna reach the Earth, those magnetic field lines are going to trap them. Most of them will be trapped, so they cannot harm us. So it's very much like a shield. The Earth is a perfect place for life to evolve. Look at this. You see, it cannot reach us. It's going to be trapped. Okay, it's going to be forced to go around those magnetic field lines. So let me ask you something. Can you see a place on Earth that is at least high in the atmosphere? You can see there where you do not have that much protection? The poles. And what do we have so special at the poles? Like a beautiful display. Northern light. So why is that northern light happening? What would we call that? Borealis, aurora borealis. Borealis? Borealis. Is that good? So those particles here are going to come here. They're going to interact with the atmosphere. Remember your chemistry class? The electrons, it's going to take the energy from those radiation. So they go to a higher level of energy. And then when they come back, they burp out light. So it could be blue light or green light, depending if the electrons belongs to nitrogen or oxygen. So if I lose my voice, that's not good. Are you see here? So these are called, if you go to space, that's what you can see. That was, you know, during the space race, during the Cold War, there was a race between the Soviet Union and the US. So one was making the first step, and then the next one, and then the next one. So the first one to go to space were the Russian with Sputnik. So then the American were second, and the American were the first one to visualize those. So those are called Van Allen belt, and you can see the magnetic field lines. So when the particles interact with the magnetic field, you have this beautiful display of colors. Okay, and then the Russians were the first one to send a man in space, Gagarin. So then the American follow. So the American were always following until they were the first to reach the moon, the first man on the moon. But the Russians were the first one to go around the moon. So it was a race. By the way, it seems that we went back to a Cold War, isn't it? Worse. I think it's worse. You know what they say, that the history always repeats itself? First it's a tragedy, but then it's worse than a tragedy. That's what they say, I don't know. I have a 3D picture, but okay. So again, you have the north and the south. Magnetic field always go from the north into the south. And you can visualize this using compass. So typical conceptual question, a magnetic field always goes from the north into the south. Can you have a magnetic monopole? No, unless you get the Nobel Prize because you find one. Okay? So everything happens like inside the Earth, you have a bar magnet. That will be the geographic north, but the magnetic south. Okay? It can be that all the numbers are moving south or yes, magnetic south. Magnetic. Magnetic, yes. Correct. Now, remember that what's happening is that it's the magnetic field interacting with each other. So you have south, okay, that will be attracted by north, but it's actually their magnetic field interacting with each other. So you can see here, it's like a stretch string. Okay, so you have potential energy into there, and the magnetic field tries to bring them together. So it's very much like you have an electric dipole, and the electric field here is like is like a spring that's being stretched, wants to bring them together. Okay, so plus wants to be close to minus, south wants to be close to north. Now, do you remember that if you have north and north, the magnetic field interact with each other, but now they are repelling each other, right? So it's like you have a spring, you squeeze the spring together, so you're gonna have some resistance. So exactly when you have minus and minus, they're gonna repel each other. What's gonna be the electric field here at the center, in the middle? If you have minus Q and minus Q, so the same charge, 0. Okay, so remember, if you have that for the test, I don't know what you have for the test, but the electric field is a vector. Okay, so you need to add vectors. So if you have this electric field from this one going down and from that one going up, they're gonna kill each other out. If the two electric fields have the same direction, you have to add them up. If they have opposite direction, you need to subtract them. Okay, because it's like adding vectors from last semesters. Is that clear? Okay, so the unit 11, so I have to follow my notes. Okay, okay, so we're good. Magnetic field, the unit for magnetic field is the Tesla. Name after Tesla. He has a very sad story because he was not trying to make money. He was really into science. He was very passionate, and he didn't bother putting patents, right? Like the opposite will be Thomas Edison. Thomas Edison was just the opposite. He was really a businessman, not the nicest businessman, but he died. Penniless, actually. So anyway, that's fine because he has a unit named after him. So the unit for magnetic field is the Tesla. Okay, so the Earth, the magnetic field from the Earth, the magnitude is 0.5 times 10 to the negative 4 Tesla. So sometimes we take a smaller unit and we use Gauss instead. Okay, so 10,000 Gauss is 1 Tesla. Okay, so it means that 0.5 times 10 to negative 4 Tesla is 0.5 Gauss. So if you have small magnetic field, you will use the unit Gauss. Okay, so 1 Tesla is 10,000 Gauss. So you have 10,000 Gauss into 1 Tesla. Is that clear? Nikola Tesla was from immigrant from Hungary, I think. So very important for those going into medicine because a lot of magnetic field inside the body from the muscles, it's going to produce that much Tesla. Oh, you see, inside human brain, 10 to the negative 13. So biology, it's a big deal. They did experiment here with lobsters, and apparently everything happens like inside their head or whatever. You know better than I do. That will be marine biology. They have like small magnets inside, okay, and they find their way using the magnetic field of the Earth. So they can orient themselves such as they don't go too far away from the shore. Okay, that's where they live. Because of course, when you are in the ocean, there is no saying, okay, this is Miami Beach here, this is South Beach here, this way you go to Fort Lauderdale. So no, you need to have a way to find the direction. And they did experiment here. You have the website if you are interested in. They try to confuse them. So they put an external magnetic field and they end up like lost far away in the ocean. That was not very nice. The poor things, but you can read about that. So even birds, when they migrate, they have like little compass inside their brain, like very tiny compass, and they can use the magnetic field of the earth to find their ways. Okay? Any questions so far? Okay, and then in 1820, and it kind of happened by chance. Remember when I talked about the first battery by Volta? Okay, and they were able to produce electricity without using a Leyden jar, without using a capacitor. So it was a big breakthrough. So all of a sudden they had access to power supply and they start to do all kind of experiment, all kinds. So you had like professor doing public lectures for the general public, showing how magic was electricity. And by chance, I don't know really how it happened, but you have Hans Christian Ørsted, who was Danish professor. He was lecturing, and next to his, so he had a wire here connected to a power supply, and he had a compass. And wow, holy moly, what happened there? The compass moved. So what do you think it means? It means what? So if the compass move, it means that you have a magnetic field. What is the source of the magnetic field? The wire. What is going through the wire? Electricity. So actually, the source for magnetism is electricity. Why do we have magnetism? Because you have moving charges. Okay, so he was able to prove for the first time the connection between electricity and magnetism. If you have electricity, if you have a current flowing inside your body, for example, then you're going to have magnetism. So that's why, for the first time, it was not electricity on one side, magnetism on the other side. It was combined into, how do you combine electricity, magnetism? It becomes electromagnetism. Exactly. That was the first time. So they understood that it was um, combined. You have to combine them together. So let me show you. I have like a simulation. Is what? So yeah, no. So when you have a current, it's going to produce a magnetic field. So to describe what's happening, you need electromagnetism, the physics of electromagnetism. So it means that electricity can produce magnetism. So listen, it's a good question. What do you think? If electricity can produce magnetism, and remember, like nature likes symmetry, what will be the counterpart? If electricity can produce magnetism, then very good. And guess what? That's how we get our electricity. Okay, somewhere in a power plant, you have like a giant magnet moving inside the coil, and that will give us the electricity that we use today. But it took like 10 years to figure out how to do it. So 1820, that's the famous experiment of Oersted. So you see, you have a power supply. So you remember, you have positive charges moving, even though it's not really true, but we love Benjamin Franklin. So let's say you have coulombs here flowing there inside the wire. That wire is going to produce a magnetic field. And what the magnetic field likes to do, does it diverge? What those magnetic fields are doing? They, they, look, are they converging? No. Are they converging like this or diverging like this? No. What they like to do? Always, always, what you see in green are the magnetic field lines. What do they like to do? They? Okay, so you mean they expand. What you say, you want to say is that the magnetic field here is decreases as you move away. That's why those lines are further away. What are they doing? Are they describing a line? It's circular. It's circular. Okay. Magnetic field like to curl. Okay, they go around. And if you have a magnet, look what the magnet is doing. What is it doing? It's following a magnet here, okay, a compass or anything that can be magnetized, like to align itself with the magnetic field, always. So I'm following the magnetic field line. Do you see? You see that or not? Right? And as you move away, you see here is more pack, and as you move away, the magnetic field is going to decrease. But the magnetic field always curls. So if you have a wire, the magnetic field wants to curl, right? Rotate. It's a rotation. Uh-oh. I don't know how to do it. Oh, let's forget. Okay, so you see the compass here, how is it relative to the wire? So the wire is in the screen, so that's going to be perpendicular. Do you see how the compass here is perpendicular to the wire? Okay, I'm going to show you um, a demo. I can show you a demo too. Are you with me? You don't space out? Here we go. So what do you have here? You have the wire. So this is your wire. Do you see the wire? Do you see the compass? Okay, so that was the 1820 Oersted experiment. Oh, look at that. Did you see how it moved? Do you see that it moved? Yes or no? Right? Perpendicular because the magnetic field likes to curl, right? So it means if I have a wire like this and you have current flowing, the magnetic field will go around and around. So let's see, this is my wire. It will go around and then another here and then another there. And as you move away, the magnetic field is going to decrease. But it's going around. So let's say I can do a demo. Uh, okay, so what is that? What do I have here? A battery, right? What's the voltage? 6 volt. What does it mean, 6 volt? 6 joule per coulomb. Very good. So you see, we review. So if you want to find the energy, you multiply voltage by charge, right? Okay, so I'm going to do something very short because the battery doesn't like that. I'm going to make a short. And now, yeah, the battery doesn't like short. So I'm going to drain. I'm draining, so I'm not going to do it a lot. So I'm going to try to make the parallel. Okay, it's almost parallel here. Do you agree? So if I connect, what should happen? Perpendicular. Ooh, do you see that? Isn't that amazing? So if you have a wire with electricity flowing through it, the magnetic field will circulate around. Isn't that interesting? So we have a source. We are sources. We are source of magnetism because you have electricity flowing. So 14. Okay? So here you can visualize the magnetic field. So each time you have a current, okay, electricity flowing, you're going to have a magnetic field circulating. It likes to curve, okay? And it will, if you have small compasses, like all around, you see it's showing you which way the magnetic field is going. So to find which way it's going, you take your right hand. You all have a right hand. Yes? Okay. So let's say the current is going, so typical conceptual question. The current is going up. So give me a thumb up. Open the hand. So that means the magnetic field is going to curl this way. If you have a current moving in this direction, open your hand. That means the magnetic field is going to circulate around this way. Okay? That's called the right hand rule. If the current is going down, it's going this way. So you have to use your right hand if it's positive charges moving. If it's negative charges moving or electrons moving, then you're going to use this way. Okay? So this is called the right hand rule. Okay? So I forgot one more thing here. Positive. Like the current is positive charges. If it's electrons moving, they're gonna produce a magnetic field, but you have to use. It's gonna be the opposite. So you use your left hand for electrons. Okay, now I would like you to use your imagination, like use your head, abstract. So you take that wire. You see that wire here? You see how you have the configuration for the magnetic field? Take that wire and make it as a coil. Okay, so like you make a coil, a loop. You make a loop of current. Let's see, think about what it will look like. So instead of having a straight wire, I'm going to have something like this. Okay, this is called a solenoid. So I curl. So can you imagine in your head what it will look like? Okay. Let's see. Did you get something like this? Yes? No? But you have to imagine you take that wire and now you curve it like this, right? And then you will get something like this. So this is called a solenoid. It's a loop of current. Okay, so let me show you a solenoid. I just show you one. Okay, it looks like this. That's a solenoid. But now let me know what is that configuration? What is it reminding you? A dipole? I don't know, magnetism. So what is that? A bar magnet. So if that will behave like a bar magnet. Is it better than a bar magnet? Yes, because you can control the magnetism. As you increase the number of loops, you're going to make the magnetic field stronger. If you disconnect the power supply, what's going to happen? It's going to go away. So you control the magnetism. And how do we call that? We call that an electromagnet. Okay, I will show you more demo, but the thing to remember is that if you have a loop of current, okay, so loop, okay, it's going around, connected to a power supply, everything happens like you have yourself a bar magnet. And you see here, that will be, so this is the compass here. That's going to be the, here. Wake up! Over there, are you awake? Yes. So that's going to be the compass here. That side is the north. So that side of the electromagnet is going to be the south. Make sense? Everyone understand? I didn't lose anyone. So this is the south. So that's going to be the north. Okay? And you see, you can see, you follow the magnetic field. The magnetic field you follow, out of the north, into the south, out of the north, into the south, out of the north, into the south. Are you with me? Okay. Are you sure? So, if you have one loop of current, you see here, the magnetic field like to circulate around always. And then if you make a loop out of your wire, you see, you have exactly the same configuration that you have for a bar magnet. So today in the industries or in medicine, we don't use bar magnet. We don't need that anymore. We use electromagnet, very good. And what is the screening? Well, they have a huge magnet that can be very dangerous. And before you do the screening, they have you take everything metallic from you. MRI. MRI has a huge magnet, and I will show you. Accident had happened before. There was this terrible story. There was a little boy. I think he was in New York, and he was 6 years old, and the technician didn't take physics 2054, and there was a tank, like a fire extinguisher in the room, and it turned on the magnet, so it turned on the MRI, and zoom, it was sucked in the MRI. So not good. Okay. So make sure if you do that, make sure there is no metallic object. It can be very strong because you can apply a very strong power supply, so you have a very strong magnetic field. So here I'm going to give you ideas if you want to do a demo easy demo to do. Okay, you see how easy it is? You need a screwdriver, and here I'm going around and around and around and around. So it's like a solenoid. So the wire has to be insulated. So here you have some very thin layer of insulation. It's called enamel, I think. So it's insulated except for the edge. Okay. And I'm gonna do something that the battery doesn't like. Okay, I'm gonna have myself an electromagnet. And okay, ready for that? So easy to do if you want to do a demo. And ooh, ooh, do you see that? Isn't that nice? So let's find out if it's a north or a south. This one. It's gonna be a south. Very good. So the other way is gonna be a no. So this is a no. It's confused. So this is a south. So this is a south. So that should be a it's a north. Right? You agree? And I can follow the magnetic field all around. So if I was to make a magnetic field, it goes, so this is the south, okay? Out of the north, back into the south. Out of the north, into the south, okay? But because inside here, you see here, it's hot. This is called a core, C-O-R-E, iron core. So what it does, okay, I could do the same thing without the screwdriver. You still have like your winding, but that core will catch all the magnetic field that want to escape and bring them inside. Okay, so you increase the magnetic field magnitude. Is that clear? So the problem with those is that even when I disconnect it gets some, it keeps some magnetism because I magnetize the inside. So for industry, we don't use those. So this is for demonstration for extra credit. Like we use something like this. Okay, so this is a solenoid. Okay, so you have wires all around, and here you have your core. So it's called soft iron. So you have this inside. Okay, so I'm gonna connect here. Go make spark, and guess what? Ooh, look at that. It's a very strong magnet. Can you see that? And guess what? When I'm gonna disconnect, what's gonna happen? You see that? So now I can control the magnetism. So why do they use that? For example, in where you have the car, the junk, you put your old car. So they will do, they take a car here with an electromagnet, they move the car and they let the car draw. Or when you are recycling, they use those electromagnets. Or inside the MRI, they use an electromagnet because you can control the magnetism. Isn't that interesting? So I have a QT here, it's a very small one. But again, it works the same way. How do we call this? If it's many loops, it's called a solenoid. Very good, a solenoid, right? So what do you have inside the MRI? You have a solenoid, very, very strong and very dangerous. Look at this one. So you increase the number of loops and you're going to increase the magnetic field. So that will behave like a bar magnet, right? So I can have Uh, that's an application. You know the old alarm? It works with an electromagnet. Well, you get the idea. Okay. So for this, you need a lot of conceptual questions. So don't space out. Okay. Uh, so here you have a solenoid. I think I have pictures for you. So that was back then when I used to teach lab. That's another thing that you can do for a demonstration. You know, when I give extra credit, it depends, you know, how much effort did you put in the demonstration. But you see this, oh, sorry, thank you. So this solenoid you can get, you know, on Amazon very cheap. You connect that to a voltage, to a power supply. And here I cut out here from a cardboard. You put iron filing on it here, and you can visualize the magnetic field. Isn't that amazing? So it means you cannot see magnetic field, but it's there. Okay? It's there in space, even though you cannot see with your eyes, but it's here. Right? Let's see. You have this one, it's the same kind of experiment. You have a loop here, okay? And with iron filing, so it's like small pieces of iron that get magnetized. So they don't move, but they get magnetized. They align themselves along the magnetic field, and you can see, you can visualize that. Okay, same thing with a solenoid here. I
Using the
have a
iron
short
filings, I'm going to show you
video.
what the magnetic field looks like inside this coil. Here I have a coil of wire. It's set in this piece of clear plastic. And all I'm going to do is I'm going to take my iron filings and I'm going to sprinkle them onto the clear plastic. And
So
then
little
I'm
pieces
going
of
to turn the
iron,
current on. I got about 20 amps of current running through that coil. And if
20
I tap
amps.
that plastic nicely, you'll see that the magnetic that those iron filings line up along the magnetic field lines inside that coil. And you can see that the magnetic field runs parallel to the length of that coil. And that is how you can see those magnetic field lines inside a coil of wire. Okay, this time I'm going to show you basically the same thing, except now I'm going to do it with two compasses that I have inside the coil. You can see now the compass needles are
Oh, that's a good
basically running
conceptual
or
question
pointing
here.
perpendicular to
So
the
that
length of the
before you
coil. This
connect
being the
it to
length
a
of the
power
coil, the compass
supply,
needles are pointing perpendicular to the length of the coil. And all I'm going to do is I'm going to shut the switch and turn my current on again, get the current running through the coil. And you can see as soon as I
you see
shut
how
that
it
switch,
moves?
that
So
now the
inside, the
compass needles
magnetic field is
react to the magnetic
uniform
field that is
about,
produced by that
and
coil that has a current
outside
running
it's
through
going to
it, and
decrease
now they
very
align
quickly.
themselves up parallel to the length of
Now, if you put
the
a
coil,
iron
because
core
that is how the
inside,
magnetic field is
it will
oriented. The
prevent
magnetic
the
field, you have a
magnetic field
homogeneous magnetic
lines
field
to leak
inside
out,
that
and
coil,
it will
and the
make the
magnetic field lines
electromagnet
run
stronger.
parallel to the length of the coil. So you can see if I open that switch, they go back to the way they were perpendicular, and then if I, and then I'm going to.
Isn't that interesting? It's very important in biology, by the way. It's a lot of magnetism. Here, again, you see inside a solenoid, the magnetic field is about uniform. Outside, it's going to decrease very quickly. Now, if you place an iron core inside, so usually it's soft iron, it's going to squeeze all the magnetic field here, and it will make your electromagnet stronger. So this is called a solenoid, and it depends on the current. So if you want to increase the magnetism, you're gonna increase the voltage applied to the solenoid, and it depends how packed are the coils. Okay, we're gonna see that equation later, but this is the number of loops per length. So more packed are all those loops, stronger is the magnetic field. Okay, so again, inside a solenoid, the magnetic field is about uniform. For a demo, you can do this, okay? You can go on Google and not Google, but YouTube, and you have many demo ideas for demo. So in that case, you see you have a core, so the magnetic field cannot leak out. It's going to be squeezed and amplified. It will amplify the magnetic field. A lot of application for that, including MRI. So MRI has a crazy, crazy magnetic field. Can be very dangerous. If that's why you don't want any metallic stuff in the room. Okay, so here also when you want to move junks made of iron, for example, you can use an electromagnet. As soon as you switch off, okay, the current, it will the things will drop. Okay, lot of applications here. For example, if you have a speaker here, you have an electromagnet, and here you will have a magnet. Okay, so that electromagnet is going to push and pull and push and pull the magnet, and that's how you're going to produce a sound. So, for example, if you are listening to music, I don't know, it goes, so the electromagnet is going to push and pull, push and pull, push and pull with the same frequency. So the magnet here is going to be pushed and pulled, push and pull with the same, and you're going to make sound waves. So that's how it works. You use an electromagnet. So Faraday's did a lot of experiment with them. So that's about history. Oh, I have one more thing to show you. So this is a solenoid. When you connect or a coil, when you connect it to a power supply, the magnetic field will not instantaneously be there. It's going to build up, okay? So you see here how the magnetic field is building up, building up, building up, right? So you can really visualize the magnetic field. And again, if you have an iron core inside, all those magnetic field will be squeezed inside, so it cannot leak out. So we call that expansion, the expansion of the magnetic field. And when you turn off the current, it doesn't disappear like this. The magnetic field is going to collapse. Okay, it's collapsing now. So when it's collapsing, do you remember how I told you when the capacitor is discharged, you have a huge burp into ink? When you are discharging a capacitor like defibrillator across your heart, the capacitor is going to burp out a huge amount of current. Remember that? So guess what? When a solenoid is going to discharge, okay, it gives you a huge surge in not current but voltage. So using this, you can make a spark to start your car. So your ignition system uses a solenoid. Okay, you charge a solenoid. When it's going to discharge, okay, you get a huge surge in voltage. It's going to burn out all its energy in the form of a voltage. If you have a very high voltage, you have a spark. If you have a spark, you can ignite and start your car. Isn't that interesting? A Tesla coil has to do with this. Hmm? When you jump start? So what is it to jump start a car? I forgot. Oh, oh, you mean when when you charge a battery with someone else's battery? No? No. The ignition system is when you start when you start your car and you need a spark to burn the fuel. It will make a spark to burn the fuel. Okay. Any question? Okay. So here you have, do you remember how we call that? Half-through magnet. Very good. And what's so special between the north and the south? The magnetic field is almost uniform. Very good. So it happens when you have a current, so it means a moving charge inside a magnetic field, it will be acted upon by a magnetic force. So the same way you have an electric force. Remember, if you have a charge inside an electric field, the charge will be acted upon by a force. Remember that? So let's review for the test. F equals QE. Okay, remember that? E, the electric field, is the force per unit charge. So likewise, a charge can experience magnetic force, but only if it's moving. Only if it's moving, then the magnetic field can pull the charge. Okay, so if you place an electric current inside the magnetic field, the electric wire will be acted upon by a force. And that's when it gets complicated. Okay, take your right hand. Okay. So it's another right hand rule. Okay, so this here is going to be the current, right? The hand is going to be your current. So the current is flowing into the screen. Yes? Yes. And then you're going to curve your hand like this, showing the direction of B. So is B this way? No, B is from north to south. Right? Oh. So the current going this way. Do you agree? Current is going this way. You're going to curve your hand towards the beam in the same direction as the beam, and the thumb will be the force. Oh, if it's too complicated, you take your 3 fingers. Work with the 3 fingers. So the thumb is the current. So current, that will be the magnetic field. The second finger is the magnetic field. So the force will be the third finger. So the force will be down. Okay? So you can use this. Okay, so your hand will be the current. You curl toward B. The thumb will give you the force. Or you can use the 3 fingers. This is I, this is B, this is F. So it has to make like a X, Y, and Z. Okay? I will let me show you an app. No, let me show you a simulation and then we'll discuss more about that. So let's see. MIT. Okay, so that will be called the right hand rule also. You see? No, forget about this one. Okay, let me show you. MIT, where is MIT? No, that's not this one. Okay. Okay, so here you have a wire, yes? Okay, here you have a horseshoe magnet, so you're going to have a magnetic field. And the direction have to be X, Y, Z. So if the magnetic field here is in the screen or out of the screen, and if the current is this way, so the force has to be up or down. Do you agree? So let's see if it works. So the force was up. So if you have a wire, okay, electricity flowing in the wire, and you place that wire inside the magnetic field, so in that case, the magnetic field will be between here, this north and south, it will experience a force. Okay, it will be deflected. Oops, you see that? Up. So what's going to happen if you change the direction of the current? It's going to go down. See that? Okay, so that means that for this unit, you're not going to have a lot of math, but it's going to be more conceptual questions. So don't space out. I see people spacing out here. Don't space out. I see you. Okay, let's try to do this one. So this is minus. For some reason, blue is plus. So the current is flowing this way, this way, this way, this way. So that will be the current flowing here. Yes? That will be the magnetic field. So what did we say? The current is flowing this way. So let's try to do this one. So we say this is the current, right? Showing the direction of the current. And then you have to bend toward the magnetic field. That's going to be the force. So which way is the current flowing? From plus, so it's going to go this way, right? So this way. Do you agree? Take your hand. Which way the current is flowing? From the plus, this way. Do you all agree with that? Okay, so it's flowing this way. Where is the magnetic field? Down? Going down or going up? Down, because it's always from north to south, yes? So electricity flowing here. So I'm curving toward the magnetic field. So where is the force? Into the screen. You see that? So let's see if it's true. Boom. Isn't that cool? Huh? What's going to happen if I switch the battery? Okay, so this is the current. You curl toward the magnetic field. The thumb will be the force. It has to follow X, Y, Z. Hello, hello. Okay, another demo.
So I have here a large magnet, South Pole, North Pole, so the field is pointing up. And then I...
Okay, listening. So this is a horseshoe magnet. Let's do that again.
South Pole, North Pole, so the field is pointing up.
Up.
And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red,
Okay, so
through the copper tube,
this
and
way.
then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. Oh, get this guy out of the way. And there you see it, floating there. Because now that I've reversed the direction of the current, current is flowing this way, magnetic field is pointing up.
So even, even us, we get confused. But this is the current. You curl like this to show the magnetic field. The thumb will be the force. Okay? Hi.
Okay. Does that make sense? Okay. The current was going, the tube was like this. Right? Okay. The north and the south. So north to south is going this way. So you're turning your hand like this. Okay, current north to south. So you're going this way.
Okay, let's do this one. Think about this one. So the magnetic field is in the screen. Yes? The current is up. Yes?
Hold on, so
Take your hand. The current is up. The magnetic field is in the screen. So you have to weigh which way you curl. You have to curl which way? Toward the screen, right? So the current is up. And you want to show. So you go like this. Magnetic field is in the spring. So the current will be the force will be this way. Right? Because the hand can rotate. So you have to rotate your hand until you curl toward the magnetic field. So first of all, that will be the current going up. The magnetic field is in the screen, so you have to curl in the screen. So the force will be this way. Okay? If the current is down, it will be the opposite. No, the current is up. So you do up, right? You do this one, right? And then the magnetic field is in the screen, the thumb will be this way. Is that clear?
you can see everyone during the last game sign language.
Current is up. Yes?
Yes.
Okay, look like this. And then this, you curl toward magnetic field.
Oh, I think this electric.
It's the back.
No, we're not going around. See what you.
So nice and harness like this in there, but push out at you. Yeah, that.
Okay?
Wrong. That's the front.
Is it not looking? Is it not looking around? This is the current. It's not looking around. It's still.
The current is this way, but that's the magnetic field of the harsh magnetic. So you are supposed to go north to south. Oh, you mean?
Yeah, is it not?
Yes, there's a magnetic field going around. That magnetic field will interact with this one, and the final outcome is going to be that force. But you have there was a magnetic field going around that wire, but that's not the question. The question is what's going to be the force acting on that wire? So again, last time, can you do all that with your hand? Up, up, up. Oh, but I don't know which way I should turn. Which way I should turn? The magnetic field is in the screen. Oh, in the screen. And that's gonna be the force. Okay? It's the pop quiz. I have another demo. Right? But look, now it will be the opposite, right? The correction is here.
I think I get it. I think I get it.